Alright, I'm Ben Johnson.
And I'm Tim Haskell.
And our project for this final design was to build an electric piano with LCD display.
To start off with some of the requirements, basically what we did is we wanted to make an electric piano where the speakers would play the desired note that the user presses on the keyboard. And we're using the DAC to produce the sinusoidal wave as an input. And we had to scale it down with the resistive divider to input to the speaker. And then the user has an option to switch between 3 octaves, which is like 3, 4, and 5. Octaves 2, 3, 4, and 5 of the musical scale by pressing button 0 on the Nexus chord.
And then the notes that it plays through is C through C in each of those octaves, which we'll show in the demo. And basically, when you update it on the keyboard and the octave, which is using the Nexus button, it updates right to the LCD screen. And we also have a preloaded song that plays continuously when you press button 2 on the Nexus board. Basically, the system block diagram was pretty similar to the previous projects. We just had to add the UART, which they kind of elaborated on a little bit. Basically, the keyboard has its own embedded system inside of it, and when you press a key, it sends a scan code, and it sends a start bit, which is like F0 and hex, and then it sends the 8 data bits, which is basically just kind of random 8 bits that the keyboard generates. Whoever programmed it made them some sequence. It's definitely not ASCII. And then it sends a parity bit, which is kind of an error checker, and then a stop bit. So 11 bits total, and that all gets sent through UART, and then we added the just use a DAC to send output to the speakers.
We're using the LCD interface that we've been using for previous labs and the microvoice software process. And then design overview. So hardware, we've kind of already talked about it. We use the keyboard, the PS2 port, and the UART light interface. The LCD, the mod, the speakers, normal stereo headphone jack, and then a little resistive network on a breadboard to scale down the DAC's input voltage so the speakers can take.
Basically, the algorithm we had to create was basically just press a key on the keyboard, and we had to figure out how the UART works in C, which is really easy once you figure it out. It's like 3 lines, and basically it reads that in, and then it goes to a lookup table, which converts the scan code to an ASCII character, and then from there we basically use the same sine wave code from our function generator with the DAC SPI, and it outputs the sinusoid to the speakers at whatever the current frequency is, which is based on the key press. It changes the interrupt rate, and the user can change the octave and note based on the buttons on the keyboard and the buttons on the Nexus board.
And then a big part of the project was to find this baud rate for the keyboard, obviously, as most people who had those projects realized. And you're just using the oscilloscope to measure the 11 bits sent by or generated by the keyboard, and then you set that in system assembly, and it works pretty well.
Basically, the first part of the integrating and testing wanted to make sure that sending the sine wave just worked to the speaker, so we just loaded up our function generator code and plugged in. We weren't really sure the voltage levels that are required to be input to the speaker, so we put it through a resistive divider, and we just had basically a divider, so the voltage it was taking off was the resistor on the voltage it was taking off was a lot smaller than the other one. It was a potentiometer, and we were just going to basically started it with like 1 millivolt peak to peak, and calculation of 3.3, and then we were going to just adjust it accordingly until we got something that worked. And then if we ran into any current drive issues, we were going to have to add a current amplifier. Luckily, we plugged it in the first time, and it worked just fine. It gave us a nice tone on the output. So then we just ported in that code, and then debugged the keyboard. We had some issues with our keyboard. It seemed like everyone else got their keyboards working. Maybe we just had a bad keyboard. Only like 10 keys on our keyboard worked. I'm not sure why, but we only needed 8 to play the 8 notes, so that worked out better.
Yeah. So basically, we just made sure that the speaker interface worked before putting it all together as well. We used our old code from the function generator to generate the sine wave on the outside, and then connecting the later. That's it. We're ready to demo. So when we start this thing up and program it, it just plays middle C at a constant tone. Turn it up for you guys. And then you can step through and like play a scale. And they're all like, you know, real frequencies, you know,
and
normal notes.
And then if we step the octave up on the next board,
then you can just, you know, play the same scale. Same idea, and we have a lower one as well, which sounds, it's kind of a whistle noise, but
probably because the speakers aren't that great on the
it's
low end.
really low. Same idea. They're all toned to real frequencies. And then we also have a preloaded sequence that we play in the highest octave. And we do this in software. I'm sure you guys can recognize this, but it's kind of cool.
And that'll just continue to play. And it updates on the screen as it plays it.
So the note and octave are just played there. And that's our project. That's it.